Our new chapter, chapter 3, gravitation. So in this chapter, there's a lot of formula that you need to memorize or know at least. So the first formula is free fall. So what is free fall? Free fall is when an object falls due to gravitational force only. So it basically it has the same acceleration. We call it gravitational acceleration. The value is 9.81 meter per second square. So it always fall with the same acceleration, increasing velocity. So that is the free fall, a phenomenon called free fall due to gravitational force. And this value of G here is for the Earth. Number 2, we learn about weight. So the weight has a formula W equal to mg. So the G used here is also has the same value, 9.81, but the unit is different, Newton per kilogram. So this is gravitational field strength. Okay. Number 3, we learn about Newton universal law of gravitation. So the formula looks like this. We have a big G, big M, small m over R square. So we introduce the new constant, big G here, which is the gravitational constant, 6.67 times 10 to the power of negative 22 Newton m square kilogram negative 2. Okay, so number 4. Okay, so number 4. Before that, this is the wrong constant. Negative 11. Okay, number 4, we learn about gravitational acceleration formula G m over R square. This works everywhere. This is also works everywhere. Means that at every planet or stars. So number 5, we learn about the mass of a planet or a star can be calculated 4 pi square r cubed over gt square. Okay. Number 6, we learn about centripetal force mv square over r. Number 7 is the centripetal acceleration v square over r. Number 8, Kepler's third law. Oh, actually, this should be. Okay, let's continue. I already erased the. Basically, number 1 is free fall. Number 2 is Newton's law of gravitation. Number 4 is the gravitational acceleration. So number 5 actually is the centripetal acceleration force, mv square over r. So number 6 is the centripetal acceleration, v square over r. Number 7 is the mass of the planet or sun, 4 pi square r cubed over gt square. Number 8 is the Kepler's third law. P square equal to 4 pi square over gm r cubed. Number 9 is the ratio, Kepler's third law in terms of the ratio, equal to R1 cube, R2 cube. So number 10 is the linear speed of satellite, G m over r. 11 is the gravitational potential energy, G m over r. And number 12 is the escape velocity, 2 gm over r. So that's the all formula that needed in this chapter. Make sure that even though you don't memorize it, make sure that you recognize each of it when we want to use it. What are the conditions? What are the values of the constants, etc., etc. So now let's move on to our question. So let's answer the first question here. Newton's universal law of gravitation. State Newton's universal law of gravitation. So basically, gravitational force is directly proportional to the product of masses of two objects and inversely proportional to the square distance between the centers of two objects. So again, this is basically from the formula Fg equal to big M, small m, r squared. So G is a constant here. So whatever on the above, we call it directly proportional. Whatever on the below is inversely proportional, since we left with big M times small m. Both are masses but different objects. Thus, we can say it's product multiplication. So product of masses of two objects. And the below one is the distance between the two centers. So this is one center, this is another center. So the distance between the two centers is r. So we have to square the r. So we have to put the square distance here. Square distance between the centers of two objects. So that is Newton's universal law of gravitation. So given two objects with mass 45,000 kg and 30,000 kg with distance between objects is 25 meters, calculate gravitational force acting between the two objects. So Fg equal to big G, big M, small m, r squared. Big G 6.67 times 10 to the negative 11. We can plug in using calculator as well. Constant 39. Big M 45,000. Small m 30,000. And then divided by 25 meters square. So when we plug in that into here, we will get 1.44 times 10 to the power of negative 4 meters. Okay. Number 3, given two persons with mass 50 kg and 85 kg sits apart with the distance of 10 meters. So we have two masses. Calculate the gravitational force acting between them. Are they can feel the force? Why? Okay, so Fg, big M, small m, r squared. 6.67 times 10 to the negative 11, 85, 50 over 10 squared. So let's see if they can feel the force. 0.67 times 10 to the 11, 5, 7, 50 divided by 10 squared. 2.83 times 10 to the negative 9 meters. So basically, this is negative 9. Basically, has a 0.0000, a many 0 as 9. And then 283. So it's very, very small force, magnitude of force that's negligibly detected. It can be negligible. So they doesn't feel the force. This is due to the mass is very small compared to massive planets or sun, and the distance is very large as well. So in order to experience gravitational force, larger magnitude of gravitational force, the mass must be larger and the distance between the two masses, the center of the two masses must be smaller. Okay. For given the mass of Earth and Moon is 6 times 10 to the power of 24 and 7.4 times 10 to the power of 22. Distance between Earth and Moon is 3.8 times 10 to the power of 8 meter. Calculate the gravitational force. Fg, big G, big S, small m, r squared. So 6.67 times 10 to the negative 11. 6 times 10 to the power of 24. 7.4 times 10 to the power of 22 divided by 3.8 times 10 to the power of 8 square. Don't forget the square. Plug in that into the calculator. We will get 2.05 times 10 to the power of 20 Newton. So it's very, very big. 20 zeros after 5. So it's very big compared to 90 before 2.283. Okay. Number 5. Given two objects as diagram below, find the gravitational force acting between the two objects. So Fg, big G, big N, small m, r squared. 6.67 times 10 to negative 11. Big M is 4.0 times 10 to the power of 7. 1.5 times 10 to the power of 7 divided by 20 meter squared. So we will get 7, 11, 47 times 0.537 divided by 20 squared. 100.05 Newton. Next part is the gravitational acceleration of field strength. Basically, both quite same concept, but we use it differently. In terms of the field strength, we usually use it to calculate the weight, whereas the gravitational acceleration is the movement, the free fall part of the concept. So the formula is G, big N, R squared. Okay, object X placed on the Earth's surface. So we are on the Earth, calculate the gravitational acceleration G of object X. Okay, so we don't need to know about the mass of object X. We just need to know the mass of the Earth. So, right, we write the formula. G equal to big G, big M, R squared. 6.67 times 10 to the negative 11. Big M is 5.97 times 10 to the power 24. R square is the radius of the Earth. 6.37 times 10 to the power of 6 square. So when we plug in that, (9.81 meter per second square). So make sure if it asks if the question asks us about gravitational acceleration, then our units must be acceleration. Okay, object X brings up to the height of 150 meters from the Earth's surface. So we stay on the Earth. calculate G of object at chapter. So we should see that the value of G slightly decreases, but not much, because 150 meter is still closer to the Earth compared to the radius of the Earth itself. So let's plug in. So now our radius is very big, but we just add a very tiny more distances, so should be negligible effect here in terms of what we add. So 6.37, plug that into our calculator. Yeah, so we still get the amount around 9.81, but the decimal places, the number of decimal after the 81 is a little bit different. Let's see, 5.97 divided by 6.37 is 6 plus 150 squared. Yeah, 9.81. So let's see here. So I managed to find the mistake here. So let's back up. Basically, it's not to the power of 26, but it's to the power of 24. So then we should get 9.81 meter per second square. So basically, what's the difference between the two above? The number behind is a little bit different, but it doesn't matter because it's still 9.81 approximately. So object X brings up to the height of 500,000 meters from the surface of the Earth. Calculate the G of object X there. So this is quite significant compared to the radius of the Earth. We should see some changes towards the value of gravitational acceleration. So let's plug in all the values. Make sure that you copy the correct value for each parameters. So plus 500,000 squared. Don't forget that. So we plug in that into our calculator. So make sure that you plug in that also in a careful manner, because all the number is very hard to replicate in the calculator. So we get 8.44 meter per second squared. Okay. Number 2, calculate the gravitational acceleration of an object placed 2,000 kilometers away from the surface of the Earth. Okay, so we still use the same formula. 6.67 as 10 to the negative 11. The man is still on the Earth, but the radius now significantly higher, plus 2,000 times 10 to the power of 3 squared. So kilometer is, the prefix is 10 to the power of 3. So plug in that into our calculator carefully. 6.37 e to the power of 6 plus 2,000 d3. And then we get, oh yeah, I forgot to square. 5.68 meter per second square. So number 3, mass of an object is 30 kilogram. Calculate the weight of the object on the surface of the Earth. Given the gravitational acceleration on the surface of the Earth is this value. So this is very direct one. So W equal to mg. Mass is 30 kilogram. So the G here is actually 9.81, but we can change it to meter per kilogram. Then when we calculate that, We got 294.3 Newton. So why I want to change it into gravitational field strength? Because we can cancel out the masses here. Just like with meter. But also you can use meter square, meter per second square here. It doesn't matter because the force is actually, the formula force is mass times acceleration. So basically the definition of Newton is kilogram meter per second square. So if you want to use the standard base unit, then you also can use the acceleration unit. But if you want to make it more clearer, the units is you can use the gravitational field strength, which is I recommended. For weight of an object on the surface of the Earth is 200 Newton. Calculate the weight of the object if placed 5,000 kilometers away from the surface of the Earth. So basically, we have two situations here, on the surface and away from the surface. So what's are the key to link between these two places is the mass, because the mass of an object is constant everywhere, whereas the weight of an object changes due to the position of the object respectively, relatively towards the Earth or the moon. So basically what we need to do first, we need to find the mass, because the mass gonna link us the object itself. So W equal to mg. So we arrange m equal to W over g, 200 Newton on Earth. G on Earth is 9.81 Newton per kilogram. Again, I use the gravitational field strength, 200 divided by 9.81. We got 20.39 kilograms. So that is the mass of the object. Then we can calculate G, gravitational acceleration, 5,000 kilometers away. So G is 6.67 times 10 to negative 11. The mass of the Earth is 5.97 times 10 to the power 24 divided by r square, the radius of the Earth, plus 5,000 times 10 to the power of 3 square. Don't forget to square. And then if we bring that down here, we will get 11 times 5.97 to 4 by 6.37 E6 plus 5,000 E3 square. 3.08 meter per second square. Again, we can change it into gravitational field strength to calculate the weight. So the weight has the same mass, but now we use different value of G. 20.39 minus answer, we got 62.81 Newton. Okay, so that's the weight of object at different position on the surface of the Earth, above the surface of the Earth. Okay, so let's move on to the next concept. Here we introduce you centripetal force. So the formula is mv squared over r, and the centripetal acceleration is v squared over r. Okay, given a load with mass 2.5 kilograms tied at the end of a string with length 20 centimeters from the center of rotation, calculate the speed of the load if the centripetal force is 200 newtons. So basically, we have to use the formula here. So we want the speed v squared. So v squared equal to fc times r divided by m. So we plug in that first. FC is 200, R is 20 centimeter, 0.2 meters. Divide by M, 2.5. You get 16, but this is square value. If you want to find the v, we have to square root that form, meter per seconds. Okay. A ball with mass 0.5 kilogram is tied at the end of string with length 20 centimeter. The centripetal force produces while rotate is 160 meter. Calculate the linear speed. Again, the same formula. mv squared over r. So we read the A. V squared equal to FCR over M. Our FC is 160, R is 0.2, change it into meter, 0.5 kilogram, the mass, 160 times 0.2, 0.5, 64. So V is square root of 64, which is 8 meter per second. Okay. Calculate the centripetal acceleration. So this is AC, V square over R. We can use the value of V square here, 64. Over R is 0.2. 64 divided by 0.2, 320 meter per second square. Okay, the next question. A car passing through a vertical loop with radius 5.0 meter without force. If another car tries to through it with velocity 6 meter per second, determine either the car can pass through or fall, given that gravitational acceleration is 9.81 meter per second square. So this is basically we want to check if our centripetal acceleration equal or not towards the gravitational acceleration, because we want to against the gravitational acceleration, so that when the car on the maximum height here, it will not fall. So what we need to do to avoid that kind of situation, the centripetal acceleration must be higher compared to the gravitational acceleration. So basically, we just need to calculate the centripetal acceleration. So the velocity is 6 squared. The radius is 5.0. We will calculate that. This is divided by 7.2 meter per second square. Since the 7.2 is less than 9.81 meter per second square, so the car cannot pass through or fall. That means the car will fall. Okay. If the value of centripetal acceleration is bigger, then the car will pass through. So what we need to do in order to increase the centripetal acceleration, we can decrease the radius or increase the speed, which is easier to do compared to the radius. The radius, we need to rebuild this structure, so it's gonna take us a long time to do that and a lot of cost. But if we increase the speed of the car, which is quite easier, then we can manage to pass through the loop. Okay, so the final part for today is the centripetal force of a planet. So what happens if a planet moving in circular motion, uniform circular motion around sun or moon around Earth? So let's see. The moon with orbital radius from the Earth center is 384,000 km rotates the Earth. Okay, calculate time taken in day to orbiting the Earth. So basically, this is the distance. The distance of the orbits, the moon's orbits compared to the Earth. So when we draw, so we have the radius here. So what we need to calculate here, we have to calculate the time taken in day to orbit in the Earth. So basically, it will give us 28 days. 28 days, but we can prove that. First, we have to calculate the uh, velocity. Okay, the velocity of the moon. So Fc equal to mv squared over r. But how are we going to find the v square here? We know that the Fc, the centripetal force here, is also equal to the Fg, the gravitational force. Okay, since it moves around the Earth, and the centripetal force is shown towards the Earth. Okay, the centripetal force experienced by the moon is shown towards the Earth. The gravitational force of the moon also shows towards the Earth. So basically, both of these values are the same because it shows the same direction. Then they must be the same as well, same magnitude as well. So equal to Gm squared. So how are we gonna do that? We need the v squared. We can cancel out m here, and then we can cancel out r as well. So the v squared is equal to the big G, big M over r. And then v is equal to square root of G M over r. So this is the linear speed formula. Use that. We can use that to calculate the orbital period. So let's take some space here. Okay. Then we can do a lot of work with our space. Gm over r. So double G is 6.67 times 10 to the negative 11, the mass of the Earth. 1.97 times 10 to the power of 24 divided by the radius of the Earth. 6.37 times 10 to the power of 6 plus the orbital radius. 1000 times 3. So we don't need to square. And then we get the value of the velocity. In that, into the calculator. We will get 0.0009.98 meter per second. So again, this is the velocity. So how the velocity going to relate with the time taken? So basically, the velocity is the displacement over time. So our displacement here is actually 2 pi r because it's circular motion. We can use the circumference formula as the distance over t. Big T is the orbital period. So if you want to find the orbital period, we can rearrange. So let's erase this part first. Rearrange the formula. T equal to 2 pi r divided by 3. So when we plug in, r is the orbital radius, 354,000 times 10 to the power of 3. Divided by v is 1009.98. So we will get the orbital period 384,000 into divided by 1009.98. Okay, a large number here because it's measured in second. 97 seconds, but we can convert that into days. First, we divide by 60. We got this, and then divide again into 60 for hours, and then divide by 24 for days. Then we get T equal to 27.65 days. Okay, so this match up with our assumption that the moon rotates around the earth, revolves around the earth approximately a month, which is approximately 28 days. Okay. Number two, the ISS in the orbit 408 kilometers away from the surface of the earth. Calculate the time taken to orbit the earth. Again, we can use the same formula here. So let's calculate the linear speed first. Equal to G and R. So G 6.67 times 10 to the negative 11, the mass of the Earth, 7 times 10 to the power 4, divided by R, 6.37 times 10 to the power 6 plus 400 kilometers away. Good. We got 7664.677 meters per second, yes. And then we don't have enough space here, but we can use the same formula. T equal to 2 pi r divided by V. R is now 408. V is 6.77 and times 280 divided by answer. We got 334.46 seconds. So how many minutes? 5.57 minutes. Okay. So basically, ISS took about 5.57 minutes to revolve around the Earth. Okay, number three, Malaysia satellite MEASAT rotates the Earth with the same period of the Earth rotation, which is 24 hours. Calculate the orbital radius that should place the MEASAT. Okay, this is quite easy because we just use the formula here, 2 pi r over t, and then we need r. So Vp over 2 pi. Again, that we have to calculate the V first. Okay. So the V, do we need the V though? V square over R and V square over R. Yeah, we can use the V, but then let's see here. Okay, so I already erased all the part. We're gonna restart again because this question is quite complicated. So basically, it asks us to find the orbital radius, but the information given is only the 24 hours, which is the T, the orbital period. So how are we going to find that? The same procedure, we need to find the velocity. So how are we going to find the velocity? So first, the velocity formula for a circular motion is 2 pi r over t. Then we need to rearrange r. So it will become Vt over 2 pi. Again, what are the formula that has r? Basically, the formula for the linear V square equal to Gm over r. So again, rearrange r. R equal to Gm over V square. So we equate these two equations here. So Vt equal to 2 pi equal to Gm over V square. Then we can cancel out the V's. Then we can rearrange V, so because we want to find the V. So when we rearrange V, it will become 2 pi Gm over V. Okay, then we can calculate V because all the information is given. We already know. So V is 2 pi, G is 6.67 times 10 to the negative 11. The mass of the Earth is 5.97 times 10 to the power 24. Orbital period is 24 hours times 3,600 seconds. So we will calculate that. 2 pi times 6.67 e negative 11 times 1.97 e to the power 24 divided by 24 divided by 3,100. We got quite large number here. 2.896 times 10 to the power 10 meter per. Okay, so let's check again so that we don't do mistakes. 11 is 1.97 into 4 divided by 24. Yeah. So then we can use the formula here to find R. R is actually Vt times R over 2 pi. In that into our calculator. We will get our R is 3.98 to the power of 14 meters. So it's quite large distances here. So basically this question is quite weird. You need to rethink about the formula that we already learned and we use it to find the orbital radius. So let's erase and move on to our next session. Okay. So hopefully the next question will give us an relief because we already do a lot of work before. Okay. So let's read. The moon with orbital radius 384,000 kilometers takes 27 days to complete the orbiting of the Earth. Calculate the mass of the Earth. So again, V equals to 2 pi R over T. We can find the V. And then we use the V to find the mass later. So let's plug in that first. Divide by 27 days times 24 hours times 3,600. We get the velocity is 1.27 meters per second, and we can use the formula Gm over R. So N equal to V square R over G. So plug in that. Make sure that you use the radius of the Earth as well. And then we get the mass 1.83 times 10 to the power of 23 kilograms. This makes sense. Next, the Earth takes 365.25 days 1 year to orbit the Sun completely with orbital radius 149,600,000 kilometers. Based on the information, calculate the mass of the Sun. Again, the same formula. Calculate the V first. Times 24 times 3,600. So the mass V square R over G. Make sure that the radius must include the orbit, the radius of the Earth. Then we got the mass of the Sun 1.9899 10 to the power of 30 kilograms. Okay, which also makes sense. Okay, that's all for today. Hopefully, you know how to use the formula that we already introduced today. But don't worry about the question 4, 5, 3, 4, 5. I think that's a little bit difficult. Even me also have to think about it a little while because it doesn't have any direct formula to calculate it. You have to derive it somewhere from the previous formula. But it's also doable, I think. But you need a lot of time to think about it. So I think that's all for today. Hopefully that we can manage to finish all the chapters in even manners that easier for you to understand. Basically, our goal here is for you to use the formula efficiently, to choose the correct formula, and to use the information to determine which formula that suitable for to calculate or determine the answer. Okay, that's all for me for today. Hopefully to see you soon. Thank you.